So finally we are ready to do analysis, and I would like to show it to you with this little example. We called it the carport. See it's a little box where at the walls there are eventually diagonals, but not here. That means here you can just drive in with your car and you have this little garage, a carport. Okay. So, referring to all the other videos, I guess you should know in the meantime how to model this and to set it up with everything what is necessary. And now we can do, as an example, linear analysis. For that we have to go to our options menu here and just select the theory. Then we don't have too many alternatives here, just only theory first order is possible. Force density method is not allowed yet, but we come to that later. Okay, that is fine. So, and yeah, then we can do analysis. We know about the grade and the things like all these things. Yeah, and now we just go further to analyze it, and here's the result. Yeah, and here with the crosshair cursor in one of the standard views, pushing the left button of your mouse and moving it up and down, we can just modify the scaling factor of the deflections, and by that we can just simulate some kind of animation about how this loading is just acting. Going back to the perspective view, we can take another view of that, and again just animating their results. We may also look at the stress resultants. Here you see all the buttons for the moments, bending moments, MY, MZ. So here we have this extra graphs. If the letters are too large, we go also here into the back, and we have the scroll down menu. We can just take the numbers a little bit smaller, the letters. We can also have a look at the torsional moments, and we have the normal forces here, and we have the shear forces in the local direction Y and Z. Remember, each of these elements, they have local element coordinate systems. So if we just take perhaps this element, and we put it on here, and you see it also here displayed here in these graphs for the stress resultants, and there can always look what is it Y and Z, the local directions, to understand what these stress resultants mean. Eventually you don't see too much in this graph. That means it is not a proper projection. Then we just take a look again here in the scroll down menu here for the element 1, for the bending moment MY, and we just perhaps take another projection. Or that one here. That was not a good one. Let's take this one here. We just may see more for the respective stress resultant. Or you take a local projection which eventually gives you the best side. You also may double click the button animate. We take it off and take it on again, on, off and on, and by that you get a nice rescaling of the graphs, and you can just see something. So these are the respective results for this element. If you would like to know it for that one, you simply pick it. We again may scale it by double clicking animate, and by that we can nicely look up what we would like to know for each element. You may move around these little graphs here, and you also may modify the size so that you can see better what is of interest for you. So that's exactly what might be of interest. Also, what you would like to know are the displacement values. For that, you just go to the respective node. You open the node context menu either by the scroll down menu, going to edit here. So then we are here in the context menu, and you simply just select the tab disp, and there you see all the respective numbers of the deflections U and the rotations around or in direction of the the related coordinates, either the global one, or if there are local coordinate systems defined, just refer to the previous slides, in direction of these local coordinate systems. That's exactly what you can receive here. What else is of interest? I don't think too much. Yeah, you are allowed, invited, of course, now to go through all these different possibilities which are not explained yet in detail. Yeah, and just to learn more. Many of these things are just more or less self-explaining. If you would like to see the support reactions, you may switch it on. Yeah, and then how to see something, but these are the support reactions here for the supported nodes. Yeah, so that is this one here. Yeah, and many other things which might be of interest. Here for the elements, yeah, you may switch on all element systems simultaneously. You see the element systems which might be of interest. That means here for the option element systems, you can switch all of them also off. Yeah? And things like that. I should not forget to explain to you the other project tables of our Excel project, and that is indeed one of the reasons that we just implemented everything in Excel and Visual Basic for application. So we are finished with our analysis. We save and quit everything. We save everything and quit Excel, and we just come back to our Excel project. There you see all these tables there. Yeah, we just have been starting in the preprocessor table, and after doing all the analysis, and we go to the respective data tables. Knoten means nodes. Yeah, there you see everything what we did. Yeah, see the generated shape in terms of the coordinates of all the 8 nodes. You see the degrees of freedom which has been automatically generated. You see here the point load at the node, in this case node 6. And scrolling to the right, you see as a result of the analysis all the displacement components, U, V, W, the displacement components, and phi x, phi y, and phi z, the 3 rotations around the global axis for all of the nodes. And to the right you see even more information about the support forces and the springs which you eventually apply, and information about the orientation of the local system at those nodes if you have generated some. Then on the system table you find everything which is of interest for the elements, for the 12 elements which you have generated. Here you have the topology, you see the individual lengths, the orientation of these elements, in terms of the cosines of the directions relative to the global coordinate system, or you see the base vectors, the unified base vectors of each of these elements. There you see the stiffnesses which we have typed in. Here you see the basic element type, Grundelement 1, so means the standard beam element rigidly joined to both of the nodes. Then the theory, first the theory, then we have line loads eventually in local or in global orientation, and we have things like self-weight, snow and wind, and eventually the direction of the wind. Here you see information about the force density, Kraftdichte force density, which we will explain later, and also here if you have given it the pre-stress force. And the next table you see the stiffness matrix, which is really a large one because we have 66 degrees of freedom. So that is really a matrix of 66 by 66 entries. Obviously not optimally numbered here, but anyway. Then we have here the vector of the applied loads. Then we have here the vector of the system displacements. That's the information what we see here. And what you see below, that's the decomposition of the stiffness matrix in a low transpose and the diagonal, and the upper, the upper and low transpose is upper, and here the lower triangular matrix if you are interested into equation system solution. Then you see the tables about the stress resultants. Here the table about the normal forces for each of the elements 1 to 12 in 1/10 steps distribution, the length, the longitudinal stiffness. Eventually, interesting for the force density and form finding technology, the antiformed reference length, the cutting pattern. Then we have the tables for the shear forces along Y, along Z, local directions. We have mx, which is the distribution of the normal of the torsional moments, my and mz. These are the information for the bending moments, again in local directions. Elements, there you see for each of the elements, which we have 12 of them. Perhaps I make it a little bit larger, you see it better. You see the 12 by 12 stiffness matrix, linear elastic, and you see even more entries which are of interest if you have constraints about the length and the bending properties, which is another point which we don't stretch too much. Then we have the two pages or two tables where we have this messages, about the latest news, what is new in Stiff. Then I have mentioned it already, the important setup table where all the problem parameters are listed which have been automatically generated or triggered by you, and your decision what kind of preference you would like to have. Alle, all means all preferences but for density and so on. So, and to come back to the basic idea of Stiff, since everything is available now in terms of this Excel table, it's the best basis you may have just to proceed with your own extensions of modeling and applying it, and can directly do further analysis and design within this environment of Excel. Just type in coding with cell apps what you would like to do. Okay, thanks for that.